The problem is from GATE 2017 mathematics paper, question number 2. The problem given is, let A be a 7 cross 7 matrix such that 2a square minus a power of 4 equal to identity, where I is the identity matrix. If A has two distinct eigenvalues and each eigenvalue has geometric multiplicity 3, then the total number of non-zero entries in the Jordan canonical form of A equals yes. So it is given only the condition that A is 7 cross 7 matrix satisfying this equation, and A has two distinct eigenvalues and each eigenvalue has geometric multiplicity 3. This is our hypothesis. Then it is asked that the number of non-zero entries in the Jordan canonical form of A. So it is asked to write the Jordan canonical form corresponding to this matrix A, and then we have to count the number of non-zero entries in that matrix. So the NPTEL reference to solve this problem is Jordan canonical form from matrix theory by Professor Chandra R. Murthy. He is from Department of Electrical Communication Engineering, Institute of Science, Indian Institute of Science, Bangalore. Even you can watch this reference video using this YouTube link. So now coming to the solution. So the only hypothesis it is given that A is 7 cross 7 matrix satisfying two a square minus a power of 4 equal to I. So it's one of its annihilating polynomial is, so x power of 4 minus 2x square plus I equal to, sorry, okay, here 1 plus 1 equal to 0, or let me remove 0, is one of its annihilating polynomial. One of its annihilating polynomial. Why? Because since this polynomial is satisfying the given matrix, that means whenever you put the matrix in this polynomial, the polynomial makes that matrix 0. So we call this polynomial as annihilating polynomial. When we have annihilating polynomial, we have a condition that then the minimal polynomial always divides the annihilating polynomial. We have that minimal polynomial denoted with MA of x always divides annihilating polynomial. So here we have MA of x divides the polynomial x power of 4 minus 2x square plus 1. That is MA of x divides this as x minus 1 whole square and x plus 1 whole square. That means minimal polynomial are, so from this we can see, as we have the minimal polynomial divides this, and it is given that as A has two distinct eigenvalues. So by this condition, what we can say is, it is given that A has two distinct eigenvalues. So from this condition, we can see the eigenvalues of the matrix A are nothing but 1 and minus 1. As minimal polynomial is a multiple of this polynomial, so every root of this polynomial should be the root of minimal polynomial, and hence those roots are nothing but the eigenvalues. So minus 1 and 1 are the two eigenvalues of A. And it is given one more condition that the geometric multiplicity of each eigenvalue is 3. From this, what we can see is we always have that we have always algebraic multiplicity, sorry, geometric multiplicity is less than or equal to algebraic multiplicity. And it is given that geometric multiplicity of 1 is 3 given, and geometric multiplicity of minus 1 is also 3. So, which is less than or equal to algebraic multiplicity of 1, and this is also algebraic multiplicity of 1. So, and since it is given, A is 7 cross 7 matrix. So, what we can observe here that from these conditions, so we have algebraic multiplicity of the eigenvalue 1 is at least 3, and similarly here it is minus 1. Algebraic multiplicity of the eigenvalue minus 1 is also at least 3. So, but A is 7 cross 7 matrix. So the total number of eigenvalues should be 7. But here we have it is 3 and it is 3, and these two are the only eigenvalues of the matrix A. So what we can say is one of the eigenvalue has geometric multiplicity as 3, and another one has geometric multiplicity more than 3, that is 4. So, or since is 7 cross 7 matrix, one of its eigenvalue one of its eigenvalues must have algebraic multiplicity as 4. Then only we can say the another one has algebraic multiplicity 3, and one has algebraic multiplicity as 4, and in total we get 7. So we suppose algebraic multiplicity of 1 is 3, and algebraic multiplicity of minus 1 is 4. Just without loss of generality, one can assume that even algebraic multiplicity of minus 1 is 3 and algebraic multiplicity of 1 is 4. One can even consider that case also, but the process is same. So when we have the algebraic multiplicity of 1 is 3 and algebraic multiplicity of minus 1 is 4, then so then the Jordan canonical form of, or let me state one more condition, from that we can construct the Jordan canonical form. We have the formula for geometric multiplicity is nothing but n minus rank of a minus lambda I. Here geometric multiplicity of lambda. But here in the case we have geometric multiplicity of 1 is 3, and that is 7 minus rank of a minus I. And similarly geometric multiplicity of minus 1 as given 3, and this is nothing but rank of 7 minus rank of a plus I. So from this we have rank of a minus I is 4, and similarly rank of a plus I is also 4. From these two conditions we have to construct the Jordan canonical form. So the Jordan canonical form of A is, and we have that if we have a Jordan canonical form of a matrix, let B be the Jordan canonical form A, then what we do is rank of A minus lambda I for each eigenvalue is equal to rank of B minus lambda I for each eigenvalue, where A is our given matrix and B is the Jordan canonical form of that matrix A. And hence from these three conditions, this condition, this, and we have one more condition that the number of eigenvalues is 7, and those are 3 ones and 4 minus ones. From all these conditions, we construct the Jordan canonical form now. So since it is 7 cross 7 matrix, so since we have one eigenvalue with algebraic multiplicity 3, so and minus 1 as another eigenvalue as algebraic multiplicity 4, so we have the diagonal entries as 1 1 1, then minus 1 minus 1 minus 1, then minus 1. So these should be the diagonal entries of the Jordan canonical form, and on the left hand side all entries should be zeros. And while coming on to the right hand side, we have that rank of A minus lambda I is equal to, okay, here for the value of lambda 1, we have this as 4, and similarly rank of A plus I is also 4. So by using these two conditions, we have to construct the Jordan canonical form. So if we have, so the question here is, what is the order of the highest Jordan block corresponding to each eigenvalue in this Jordan canonical form? So if we assume the Jordan canonical form, sorry, the Jordan block corresponding to the eigenvalue 1 is 2, then then here we get 1. In that case, if we observe rank of A minus lambda, sorry, A minus I, we get that we get the we get rank of A minus I as 5. If we assume there is a Jordan block of order 2 in this Jordan canonical form, then rank of A minus lambda I is 5, but it is given that rank of A minus I is 4 only. So there cannot exist a Jordan block of order 2 in this Jordan canonical form. So highest order of the Jordan block corresponding to the eigenvalue 1 is 1 only. So the Jordan block corresponding to eigenvalue 1 is of order 1 only. So similarly, when we look at the eigenvalue minus 1, so if we assume there is a Jordan block corresponding to the eigenvalue minus 1 is of order 2, then what happens? So if we assume here it is 1, so that means I am assuming there exists a Jordan block corresponding to the eigenvalue minus 1 of order 2. Then we have rank of A plus I is equal to, so we get all these entries becomes 0, these 4 entries, and we get these 3 are non-zero entries, and here one non-zero entry. So we get this rank of A plus I is 4. So this is a possible. But what if we assume there exists only Jordan block of order, highest Jordan block of order 1 only? Then what we get is, so our matrix will become as this. So in that case, we have rank of A plus I will become 5. Sorry, rank of A plus I will become 3. But that is not correct, as we have rank of A plus I is 4. So what should happen is the Jordan block corresponding to the eigenvalue minus 1 is of order 2 only. So we get one entry here, 1. and all the remaining entries as zeros. You can you can ask one question here, that why we are considering the Jordan block up to order 2 only. Why we cannot consider the Jordan block of each eigenvalue can be 3 or can be 4 here. But if we look at minimal polynomial, so minimal polynomial is dividing this polynomial, and here the power of each factor corresponding to each eigenvalue is of order 2 only. That means, so the Jordan block corresponding to each eigenvalue in the Jordan canonical form is at most of order 2 only. So the Jordan block corresponding to each eigenvalue in Jordan canonical form cannot be more than 2. So if we check up to of order 2, it is enough. So this is our Jordan block, and hence we can observe here that the number of non-zero entries in this matrix are 8. Entries in Jordan canonical form. Jordan canonical form of A are 8. So answer is 8.